ahead and get started with some review of things we've talked about over the last couple of days. We talked yesterday about a group of geometric plane figures that are bounded by straight lines. It's a very general term. What do we call these geometric plane figures bounded by straight lines? Kendall? Polygons. Now, if it's bounded by specifically 3 straight lines, Audrey, we have a triangle. And we talked about all kinds of different triangles. We talked about isosceles triangles, Chris, which, what are those?
At least 2 equal sides.
At least 2 equal sides. We talked about scalene triangles,
No
Ethan.
equal sides.
No equal sides. We talked about equilateral triangles, Kendall. All sides equal. So would an equilateral triangle be isosceles?
Wait. No.
Yes. Because it has at least 2 equal sides, doesn't it? If all 3 are equal, it has at least 2 equal. Would isosceles necessarily be equilateral, Audrey? It could be. Doesn't have to be. Because if it only has 2 sides equal, it would be isosceles, but they're not equilateral. So the 2 aren't necessarily, they're certainly not exclusive. There's some overlap, but it's not bidirectional. Yes, sir, question?
I have a question. Are we going to be quizzing on these concave polygons too? Because I know you said that we aren't going to be using them.
You need to know the term, which we're going to get to in just a moment, but you aren't actually going to be working with any of them in class, no. We said that you've got triangles like, equiangular triangles. What are equiangular triangles, Chris?
All three angles are equal.
All 3 angles equal. What if 2 angles are equal? Ethan? Then, based on our observation, it would appear that 2 sides should be equal, and therefore it would be isosceles. Good. What if one of the angles is an acute angle? Audrey? Just a triangle. All triangles have at least 1 acute angle. What if it has 2 acute angles, though? No, all triangles have at least 2. Okay, what if all 3 angles are acute? No, then it's an acute triangle. Audrey's like, man, all the other math classes I took with him, he just taught me how it was. Now he's trying to trick me. I'm trying to get you to think, right? 1 acute angle, that doesn't tell you anything. 2 acute angles, that doesn't tell you anything. 3 acute angles, now we know it's an acute triangle. What if you have a couple of obtuse angles? Kendall? I couldn't keep a straight face. I did such a good job with her, I keep doing it. What if we have a couple of obtuse angles? Then it ain't no triangle, right? Triangle can't have 2 of them. So 1 obtuse angle, though, in a triangle.
Obtuse.
No, she's like, he's trying to trick me. No, this really is the definition of obtuse triangle. What about a right angle in a triangle? Genesis? It is a right triangle, good. In an isosceles triangle, what do we call the non-equal side? Or how should we draw the non-equal side? Chris? In an isosceles triangle, assuming there's just 2, there could be 3, but assuming there's just 2 equal sides, the non-equal side should be drawn as the base, and the equal sides then we would refer to, Audrey, as the legs. In a right triangle, there are legs also. What are the legs in a right triangle, Ethan?
The 90-degree line, the one like coming down like that.
The 2 perpendicular sides that form the right angle. There we go. And what about the side that doesn't form the right angle? It's across from the right angle. Genesis? The side across from the right angle? Chris?
Hypotenuse.
The hypotenuse. The hypotenuse. We said in a triangle, all the vertices are connected together, which gives a triangle great strength. Other polygons, however, 4, 5, 6, however many sides you want, there are non-consecutive vertices, and you could join them with a line. What do we call a line that joins non-consecutive vertices in a polygon of more than 3 sides? Kendall? Genesis. A line like that joins non-consecutive vertices. Audrey. Chris.
Diagonal.
Diagonal. It's called a diagonal. Now again, we'll normally just write diag because we're too lazy to write annul, but diagonal. And this polygon here, by the way, all of the angles are either obtuse. They pretty much all look obtuse. But if all the angles are acute or obtuse, right, basically no reflex angles, like this one, we would have a polygon that we'll work with in this class that we call, back to Genesis, a polygon that doesn't have any reflex angles in it. Kendall?
Concave.
Other one?
Convex.
Convex polygon. You might be thinking back to your days when you first learned about convex and concave. I think you talked about it with mirrors, perhaps in a science class, or anyway, convex has the of bulging outward. So this polygon just keeps bulging outward. But a polygon that does something weird like this, where it caves in the middle, here you have this reflex angle as an interior angle. Again, it kind of caves in one spot. That's how you'll remember concave, so just remember convex is the other one. But again, we're not going to be working with concave polygons. We'll be working with convex polygons. I did talk about a type of polygon. We're going to look at these a little bit more today. Polygons that all the sides are equal. What's that word, Audrey? For all the sides equal. Equilateral. And all the angles are equal, Kendall. Equiangular. Well, if a polygon is both of those, both equilateral and equiangular, we have a polygon that is, Chris?
Center of the polygon. Is it called like center of the polygon or something?
No, the polygon itself is called a, anyone? Regular. A regular polygon, both equilateral and equiangular. By the way, remember we said with a triangle, if all the sides are equal, then all the angles will be equal. Do you think that's going to be true? So an equilateral triangle that is also equiangular is a regular polygon, correct? Wouldn't that be true for anything, that if it's equilateral, wouldn't it have to be equiangular? What do you think? No? Can you think of an example?
If it's the same, like.
If we have a polygon and all the sides are equal, wouldn't all the angles have to be equal? Is equal size, equal
Not
angle?
necessarily.
No?
I can't think of maybe an example, but like if you have a triangle and the sides are the same length, they could be placed at different angles. They'll still be the same length, won't they?
No, certainly not. No. Because if you try to change the angle at all, they would end up crossing over each other if they kept the same length.
So it's not possible.
So we're saying it's not possible. What about a rectangle? That's a polygon, correct? Notice all the angles are equal. And they're all right angles, aren't they? Is it equiangular? Is it equilateral?
No.
No. Can you think of a polygon, a four-sided polygon that is equiangular and equilateral? A square, right? A square. All the sides are equal and all the angles are equal. Those of you who are here in junior high, can you think of a four-sided figure that's equilateral, has all equal sides, but not equiangular?
Diamond? Or not a diamond, what is it called? It's called like a robe or something?
Rhombus, there we go. Yay, the two who weren't here in junior high. Okay, the rest of you. Rhombus, come on now. Good, a rhombus has all the sides equal, but the angles aren't equal. So it's unique. The triangle, equilateral and equiangular, the one predicates the other. Not true for all polygons. So that's why regular does have to have both parts of the definition. So equilateral and equiangular. Interestingly, an even number of sides means the two could be exclusive. But an odd number of sides, they always have to be the same. So a pentagon, if the sides are equal, the angles will be equal. Hexagon, 6 sides, you can have equal sides without equal angles, vice versa. So anyway, that's just a little note for later. Toss that thing aside. We said if we have a regular polygon, there will be a point in the exact center of that regular polygon. How did I say we would define the exact center of a regular polygon? Ethan?
Middle.
That doesn't sound like a very
Middle.
geometry-ish definition.
Center.
Middle. Yeah, that's what I just said. It's, how do we define the center? How would I actually locate the center? How do I know if that's really the center? It kind of looks like the center, but how do I know?
Isn't it the place where the middle of all sides meet?
Don't you like draw lines or something? Like, is that angle?
You're getting closer,
An
actually.
angle to the other side.
The angle bisectors, where the
Oh.
angle bisectors all come together. So if we took the time to actually bisect all of these angles, where they meet up is where the center of the regular polygon would be. Doesn't sound like we studied these terms last night. May just be me. Make sure you're studying every night over terms. I want to get back though to that paper that you had at the end of the hour yesterday. I told you, put this paper aside, save it, don't lose it. We were just drawing some figures, we were measuring angles, we were adding them up. Some of us still working on getting good with using the protractor and reading it accurately. But we want to practice with a 6-sided figure. So take out your straight edge and make a figure, a hexagon is what it's called, that has 6 sides. Doesn't have to be beautiful as long as it has 6 sides. That said, beautiful may make your life a little easier.
You said 6 side?
I did say 6 sides. I also said hexagon. Take your pick. 6 sides or hexagon, it's up to you. That would be octagon. Oh my. Alright, once you got your 6 sides, draw it nice and big. Draw it big enough where you're going to be able to read your compass, or I mean your protractor rather easily. Measure the angles carefully, add them together. May want to use your calculator to add them up, as we're getting into some bigger numbers at this point, because there's just more angles. Almost all these angles probably will be obtuse this time. It's going to be hard pressed to fit an acute angle into a hexagon. Smart. This is just extending the lines out to make it easier to read. Draw your hexagon. Figure out the angles. Again, almost all of them should be obtuse. Then add them all together. Yeah, it's possible to get one. It's just not common to get one. And at most, you typically would only get one. I guess. No, you could do it with more. For instance, something like this. We start with a really long base, for instance. Come up. 1, 2, 3, 4, 5, 6, and you're gonna have some pretty flat looking angles to make that happen. But here I've got a couple of acutes in there. So again, it's not impossible, it's just typically not the case. Alright, Audrey, you have your total? Alright, what's your total? 703 degrees. Kendall, you have your total?
716.
716 degrees. 725 degrees. That's what I had also. We need a couple more.
Almost there.
This one here, pass your pencil. Actually, let me just rotate it this way. Just 120 here, you see how it's a few degrees, but it's past 120, isn't it? So it wouldn't be 117, but 123. So that'll change 6 degrees greater for that angle, which would put you at 6 degrees, 709 then at that point, Audrey? We got those 6 degrees in. All right, Ethan's added them up. Genesis has hers. 617. That does sound kind of small. Let's see if we can find the problem. This one looks like it's way more than 96. Let's see if we can figure it out. Here's the vertex line. So it looks like it's at 116, 117-ish. That's gonna have about 20 degrees. So check some of your other angles there as well. Ethan, what'd you get?
722.
722. All right. If you were to get it perfect, you'd get exactly 720 degrees. Now, you've been kind of taking my word for it, and that's actually something I don't want you to do in this class, is to simply take my word for things. I told you that 4 sides should be 360 degrees. I told you yesterday that 5 sides should be 540 degrees. Now, again, I don't expect you to simply take my word for it because, again, our observation, our measurements are all over the place. I think, though, we've done enough measurements to realize there's going to be some human error in our measurement, right? Now, it's easy to misread things. How could we actually come to the conclusion that there should be 720 or 360 or 540? Well, consider this for a moment. If I were to draw from this vertex all the possible diagonals, how many would that be?
Only one.
One.
One, yeah.
And when I draw that one diagonal, I take my 4-sided polygon and I break it down into a pair of triangles. If I were to add all the angles of the triangle, we said those should add up to 180. And if we were to add all of these angles together, they should add up to 180. 180, 180 would add up to 360. Another way you could think of that is if you wanted to think of a square or a rectangle, 90 plus 90 plus 90 plus 90 would have to be 360. But the better reasoning is because you draw that diagonal. We'll consider this for a moment. How many diagonals could I draw from, say, that vertex? 2. I can draw 1 here and 1 here. How many triangles? 3. How many degrees in each triangle? 180, which includes this little angle, and this little angle. But then the rest of that angle, and this part, and that part would also be 180. And then the rest of that angle, and all of this angle would also be 180. 3 180s equals 540. So when I come here and I say it should be 720, well, pick a random vertex. How many diagonals can I draw?
3.
3.
1 here, 1 here, 1 here, which gives you how many triangles?
5.
4. 1, 2, 3, 4 triangles. Each one should have 180 degrees in it. Yes, sir.
So every time you add an extra line, you're just adding 180.
Ah, we make a conclusion then. Well, let's go ahead and make some conclusions then. Take a blank sheet of paper out. This is going to go into the class notes section of your notebook. Yeah, good call, Chris. Every time we add a line or add a side to the polygon, it seems to add 180 degrees. So let's look at some numbers and see if we can algebraically represent some things. You're probably going to want to turn your paper sideways so you'll have room to put this chart on the paper. We're going to make several columns here. The first column that I want to have is a column that says number of sides. We're going to make some observations here and see if we can come to some mathematical conclusions. I also want to have number of interior angles. The number of interior angles. Then I'd like to have number of diagonals, that's diags, from one vertex. Number of diagonals from one vertex. number of straight angles in the sum. Finally, the sum of the interior angles. And leave room for 2 more columns, which we're going to add momentarily. So we're going to have a total of, 7 columns in this chart. So give yourself room for 2 additional columns at the end. And let's think about some things we've already observed, okay? We start with a triangle. 3 sides, correct? How many angles, class? 3. Very good. Okay, this is not a trick question. 3 sides, there are 3 angles. How many diagonals can we draw from a vertex in a triangle? 0. You cannot draw any diagonals in a triangle. How many straight angles are in the sum of the angles of a triangle?
0.
How many straight angles in the sum? 1. In fact, our principle 12 said the sum of all the angles of a triangle equals 1 straight angle. That's 1 straight angle. So therefore, we know the sum of all the interior angles of a triangle is how many degrees? 180 degrees. We said though if we have 4 sides, a quadrilateral we call it, how many angles?
4.
4 angles. How many diagonals could we draw from a single vertex? 1. And that 1 diagonal divided the polygon into how many triangles? 2. So therefore how many straight angles? 2, which was how many degrees? 360 degrees. We said if we have 5 sides, a pentagon, how many angles? 5. How many diagonals could we draw from a single vertex now? We're up to 2 diagonals, which means how many triangles? 3, which means 3 straight angles in the sum, which was how many degrees? 540. The last thing we just drew was a 6-sided figure, a hexagon. How many angles? 6 angles you had to measure. How many diagonals could be drawn? 3 diagonals, giving us how many triangles?
4.
So therefore, how many straight angles in the sum?
720.
Well, how many straight angles?
Oh, sorry.
4, and therefore how many degrees?
720.
720. Okay, now let's say though, because we could go on forever with this, couldn't we? Because you could have a polygon with an infinite number of sides. It'd just be really small and the angles would be really big. Let's just say we had n sides. We'll represent it algebraically. How many angles would be in a polygon of n sides? N angles. The number of sides and the number of angles match. How many diagonals could we draw from a single vertex if the polygon had n sides?
And X.
2n.
Notice, 3 sides, 3 angles, 0 diagonals. 4, 4, 1, 5, 5, 2, 6, 6, 3.
And 4.
What's the progression here?
4.
To go from the number of sides or angles to the number of diagonals, what do we have to do?
Plus 1. And
No,
plus
to
1.
go from this to this, we add 1. To go from
Minus
this
3.
to go from here to here, what do we do?
Minus 3.
Minus 3. So if there are n interior angles,
And minus 3.
n minus 3 diagonals. So you can draw as many 3 fewer diagonals than you have sides. Does that make sense? All right, now, how many triangles or straight angles formed by those diagonals?
You're minusing 2 every time, so you would do n minus 3, 2.
N minus 2, good. 1 more triangle than you have diagonals. Or you could say the number of sides minus 2. 3 to 1, 4 to 2, 5 to 3, and so forth. So we'll say n minus 2. And of course, that's the number of straight angles, and every straight angle is how many degrees? 180. So basically, to get the sum of the interior angles, what would we do with the number of straight angles to get the degrees?
N minus 2 plus 180. N minus 2 times 180.
N minus 2 times 180 degrees. Circle this and star it. You're going to memorize that little formula. There are n minus 2 times 180 degrees in the sum of all the angles of any polygon. So I can give you any number of sides, and without drawing it, without measuring, glory, without any of that, you can tell me how many degrees are going to be in the sum without having to make any human error. Now, again, if you're up for the challenge, like, I wonder if I can get it perfect. You figure out how many there should be and then measure and see if you can get it. But we know how many degrees should be in the sum of any polygon just knowing the number of sides. 10 sides, minus 2 is 8 straight angles times 180. 15 sides, minus 2 is 13 straight angles times the 180 gives you how many degrees. So this tells us the sum. And for most polygons, this is as far as you can get. But if you have a regular polygon is a polygon that is both equilateral and equiangular. So if all the angles are equal, and if I knew what the sum of all of them was, well, let's think for a minute. Triangle, how big are all the angles in a triangle, in an equilateral triangle? 60, right? Because equal sides, equal angles, 60 all around. How about this? Each angle of a regular polygon. If we want to find each angle of a regular polygon, well, we said for a triangle, 3 sides, that's going to be 60 degrees. We said our regular quadrilateral is called a
Polygon.
regular polygon of 4 sides. What do we call it? What would Chloe call it?
Square.
Square, right? It's a square, right? How many degrees in every angle of a square? 90 degrees. Because the sum of all the angles is 360, and they all have to be equal, so you simply divide it by 4. So if we wanted a regular pentagon, all the angles of a regular pentagon have to add up to 540, but there's 5 of them.
120.
You were a little off on your division. 108.
Oh.
5 goes into 5 once, 5 goes into 4 is 0, then 5 goes into 4D 8 times. 108 degrees in each angle. 6 sides, a regular hexagon. We know altogether the angles all add up to 720, but there's 6 angles. How big would each angle have to be? 120, good. 72 divided by 6 is 12. Tack on the 0, 120 degrees. In general, all we have to do is take the sum of all the angles and divide by how many sides, right? How do we represent algebraically the sum of all the angles, class? Good, Genesis, you read well. N minus 2 times 180. The rest of you can read as well as Genesis, class. How do I represent the sum of all the angles?
N minus 2 times 180.
Good, N minus 2 times 180. But then we said we're going to divide it by how many sides there are. Well, we're using N to represent our number of sides. So to find each angle, write this down. N minus 2 times 180 degrees all over N. And we need to memorize that formula. Now again, that only allows you to find each angle of a regular polygon. If I said, how many degrees are in each angle of a 9-sided polygon? You don't know. There's no way to know. Because all the angles could be different. It would be a trick question, wouldn't it, Audrey? That would be very mean of me, wouldn't it, Audrey? Especially on a quiz or test. But if I said, find each angle of a regular 9-sided polygon, well, suddenly you could do it, right? Take the 9 sides, subtract the 2 to get the number of straight angles, times 180 and divide by the 9 sides again. And we could get that. I want you to also think, though, for a moment, if I have a regular polygon, we talked about finding the center of a regular polygon. We said we would bisect each of these angles. And if we were to bisect all the angles, they would all come together at a point we call the center of a regular polygon, correct? Here's a question for you. There were 5 sides, there were 5 angles, there are 5 bisectors. How many angles are formed right here? 5, right? 1, 2, 3, 4, 5, 5 angles, correct? How many degrees from start to finish?
360.
360. Now, is that because there's 5 sides that there's 360 degrees?
No.
What if there were a whole bunch of sides? How many degrees would be in the middle? Still 360, correct? So if all of these angles are equal, stay with me here, then all of their bisectors, bisected pieces would have to be equal because halves of equals are equal. So this triangle here has 180 degrees in it. Some of those degrees are here, some of those degrees are here. This triangle also has 180 degrees in it. Some of those degrees are here, some of those degrees are here, but these two numbers are the exact same as these two numbers. So what must be true of these two angles?
They're equal.
They have to be equal, because you're taking straight angle equal to straight angle, you're subtracting equal quantities away from those straight angles, you must be left with equal quantities, correct? And that's going to be true not just for these two, but for each of them. All these angles would have to be equal. If it's a regular polygon, you're finding the center, correct? So, how might I find, let's just take it's a pentagon, right? 5 sides. How would I find how many degrees are in just one of these angles?
Divide 5 by 360.
Other way around.
Divide 360 by 5.
Right, take the 360 degrees, divide by the 5 angles that are there. Do that on your calculator real quick. 5 divided by 360 divided by 5. 72 degrees. So our last column is going to be the measure of each angle at the center of a regular polygon. Each angle at the center, yes, of a regular polygon. And we said for a 5-sided figure, that's going to be 72 degrees. What about a triangle? How many angles would be at the center of a triangle, class? 3. 3 bisectors would form the 3 angles at the center. So how big would each angle at the center be of a triangle? Well, 360 is the total, but there's 3 angles there. So each angle would have to be 120. Picture it here for just a moment. We've got an equilateral, pretend it's equilateral, triangle. We bisect all the angles. Well, we know there were 60 at each of these angles, correct? But we bisected them all. So how many are in each of the little pieces now? 30. There's 30, there's 30, 30, 30, 30, 30. Okay, well, that's a total of 60 down here, which leaves us with 120 right here. 120, 120, 120. There's your 360 degrees at the center. What about a square? That's your regular quadrilateral.
90 degrees.
Right, so that means that in a square, if you were to bisect all the angles, these bisectors would end up forming little right angles. In other words, the bisecting lines would be
45.
perpendicular to each other. Now, Chris, you were thinking down here, they would make 45-degree angles, right? 45 here, 45 here for the total of 90. But these bisecting lines would end up being perpendicular to each other. They'd give you 90 degrees at the center. What if there were 6 sides? How many degrees at the center? 60 degrees at the center. And in general, we said, what do we do to find the number of degrees at the angle in the center?
And minus 2 times 1.
No, angle at the center. We take 360 and we divide by however many sides, right? So we could say 360 degrees over n. And there's a third formula to memorize. Now, I want to make an observation here. I want to lock in on these last 2 columns. I want you to look at the numbers side by side. 60-degree angle, 120-degree angle at center. 90-degree angle, 90-degree angle at center. 108-degree angle, 72-degree angle at center. 120-degree angle, 60-degree angle at center. Any thoughts on the relationship between the numbers in those columns?
Because 2 of them.
Multiply it with divide.
But 108 and 72 looks like it's out of place.
It does kind of look like it's out of place, but it's not. Not for the relationship that's there.
They're all even. I mean, that's. Yeah, I'll give you 180.
There we go. They add up to 180. In other words, they are going to be what?
Equal to
What's that word? It means they add up to 180, or a straight angle. Supplementary. The angle at the center is always going to be supplementary to each angle of the regular polygon. Think about why that is. Remember, we said if we had a regular pentagon, we said each of these angles is going to be 108, correct? So when you bisect the angles, each 108 gets bisected into what? A 54 and a 54, but what is that? That's 108. You only have 180 degrees here. So the angle at the center is going to be add up to 180 with the two bisected pieces, which the two bisected pieces together will equal this whole angle. So of course they're going to be supplementary. So if you happen to be finding a little shortcut, just take the supplement rather than using the formula. But yeah, an interesting observation there that we can make. So we're going to come back to that in just a little bit. For now, put that in the class notes section of your notebook. You'll want to look that over this evening. Make sure you work on memorizing those formulas. We're going to come back to them. But first I want to show you a couple of ways in which we can actually draw regular polygons. How we can draw regular polygons. Now, I didn't use the word construct because we're going to have to use a protractor. If you're using a protractor, you're not constructing. You are drawing. Okay, so little clarification there. But let's start with that polygon of 5 sides, a regular pentagon. How could we draw a regular pentagon? Well, remember we said for a pentagon, how big is each angle going to be, class? You can cheat and look at the chart real quick again. How many degrees in each angle of the pentagon if it's regular? Pentagon, 5 sides.
72.
That's each angle at the center. Each angle then would be the supplement, or 108. So we want 5 108 degree angles. So one way in which we could draw a regular pentagon would be to draw a line, and at one end of the line, make a 108 degree angle, 108. And at the other end of the line, make a 108 degree angle, 108. And draw the sides nice and why is there playing tricks on me now? Yep, 108. Yep, 108. Then what we need to do, remember, that is going to help us to make equiangular, getting some equal angles, which we'll continue to do, but it doesn't make it equilateral, right? So for that, take your compass. Measure your baseline and mark off that exact length on the sides. And if you wish, scribble off the extra. So draw 108 at each end of your baseline. 108 seems just a nudge off there. Pencil. Alright, so here's 100, here's 110. It's 2 degrees shy of 110. And and then at this end, okay, here's 100, here's 110, so 100, 110, you get 2 degrees shy of that. So, alright, good. Ah, you did make an awfully big base, didn't you?
Want me to redo it?
Yeah, well, leave one end, leave this end, and erase all of this and just make a new end, and put your 108 there. Okay, good, good. Did you, and you went ahead and erased the excess, as opposed to, is that equal? You measured this baseline, right? And you make this line the same length, and you make this line the same length. Maybe you erased a little too much. Yeah, you're going to have a hard time with that long of a base, because the lines will have to come up, you know, that far in each case, so might not fit on the paper. The next thing that we do then is, well, draw another 108. So I'm going to come here and make another 108. And come here and make another 108. And if I want to, I could measure to make sure the top angle is also 108 degrees. And I'm actually slightly over, it's like 111, so my drawing's not perfect. The other thing I could do is, if I still have my compass open, see if those other lines are the correct length. Not quite. So this is, I would say, an obnoxious way to do it. It's one way to do it, I suppose, if you're really, really accurate. It's not the most efficient way, I would say. There's a better way. Instead of using the 108s all the way around, how big was each angle at the center supposed to be, class? 72. So instead of doing that, why not start at the center and work your way outward, like this? Start with a line, don't make it too long, kind of toward the middle of your paper. Start with a line, don't make it too long, maybe 1.5 inches is all you should need. Though Genesis, you're gonna have to make yours longer to get through the edge of your protractor at least. What I want you to do is, instead of doing 72, 72, 72 all the way around, why not do 2 72s at the same time? It's one less time I have to move my protractor, correct? So let's make 72 and 144, which is 2 72s. And we're going to actually draw the lines that go outward from the center to the vertices. So I've got 72 degrees and 72 more degrees, giving me the 144 I marked. Now, one time, rotate the protractor and do the same thing again. Another 72 and another 144. You can check and make sure you actually have a 72 as your last angle, and I have more like a 74 because my lines are just a nudge off. And that's going to get me all the equal angles, theoretically, as long as it's done perfectly. It's going to get me all the equal angles at the center.
How did you rotate your projection?
Okay, so I started by doing both 72 and 144 in this position. Once I had both of those lines, I rotated it here and did another 72 and 144. Again, if you're working at home, you have the luxury of pausing this video and catching up. Those in the class don't, and we are up against the clock a little bit here. The last thing that we need to do, well, we can't measure the sides, but if the legs, remember we said if you draw those little bisectors, it's going to make a lot of little isosceles triangles. As long as the legs of the isosceles triangles match, the bases, sides of the polygon should match. So I'm going to measure any amount on my shortest piece and mark off that amount all the way around. You could just draw a circle, but I'm lazy. And then join these points together, like so. And as you do, you'll be forming a regular pentagon. And I feel like this method is easier because you have the potential to knock out multiple angles at once. And there's another regular pentagon.
Knocked him out with a little funky.
Yeah.
Yes, something ain't right. So you start here, and you measure 72, kind of. Now 144 is on, then you rotate it here, and you measure 72, which would have been over here. You got the wrong 70. Starting from here, 0, 10, 20, 30, 40, 50, 60, 72.
What I did is
And 140. You looked at this one, yeah.
no, what I did is I did it from right here.
Oh, no, wrong one. In continuance. In continuance would have gotten it for you. Alright, now, I will say, either way, odd number sides are a little bit harder to work with. But you remember the square? I showed you that if you were to bisect the one angle, bisect the next angle, bisect the next angle, you essentially end up with 2 perpendicular lines. If you were to have 6 sides, just a rough sketch, bisector, 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 you really end up with 3 lines. And we can use that to our benefit. Let's do a 6-sided regular polygon now. Let's finish out with a 6-sided regular polygon. This one's going to be much quicker and easier to do. First of all, 6 sides, 360 degrees at the middle. How many degrees in each angle at the center? 60. 360 divided by 6 of them. Start with a decently long line, maybe 2.5 to 3 inches long. 2.5 to 3 inches long. And pick any point kind of toward the middle-ish, midpoint, approximately, doesn't have to be perfect, but approximately the midpoint. This is going to actually be the center. Because all you need is 60 degrees, 120 degrees, and oh yeah, 180 would be the next 60, wouldn't it? 60, 60 more is 120, 60 more is 180. But when you draw these angles, because they form straight lines on the other side as well, unlike the odd numbers, just draw them through. And boom, you've got all your angles at the center done just like that. Now measure any amount you want and mark all the way around. And connect those dots. So even number sides of polygons, because you can just connect draw through, works much easier. Boom. It kind of looks like the side view of a TIE fighter.
I was actually about to say that.
Your geometry teacher might be a Star Wars nut if you draw TIE fighters in geometry class.
Yeah, you just gotta.
Looks like the drawing.
Just need a dodecahedron to go inside on the other side of the chalkboard and another one. We're good.
There's like 1 million of those in each episode.
It looks like the drawing plans for the Death Star. Actually.
We are going to do a Death Star construction later on this year.
Wait, what?
You're joking.
No. We don't call it a Death Star construction. That's what it looks like. That's what everyone calls it. Poor Genesis. All right, now your homework for this evening is to study. Study the chart. Know those 3 formulas. Let's review very quickly in the 10 seconds we have left to find the sum of the interior angles of any polygon class, n minus 2 times 180 degrees. To find each angle of a regular polygon, we're going to take that sum and divide by how many there are. So my formula is n minus 2 times 180 degrees over n. And to find each angle at the center of a regular polygon. Remember, how many degrees total at the center? 360. So it's just going to be 360 divided by n. Okay, know those formulas, study, spend some time studying. We're going to practice with these formulas tomorrow, do some math with them. Don't forget, we are looking ahead at a test coming up Monday in lesson 16. Test coming up Monday in lesson 16. You are dismissed. Have a wonderful rest of your day.